Picture this. You've spent your whole life obsessed with one question. What's actually inside a black hole? You've read every book, watched every documentary, and somehow, impossibly, you get your shot. A ship drops you at a safe distance from Sagittarius A star, the supermassive black hole at the center of our galaxy. You climb out and you start falling. There's a word for what happens next: compression. Your fall will take about an hour, and it will end in your death. The first thing you'd notice isn't darkness, it's light. A disk of superheated plasma spinning around the black hole so fast it's nearly moving at the speed of light, glowing blue-white and blasting out radiation that could cook you instantly. One side of that disk looks brighter than the other. That's the Doppler effect, the same reason a siren changes pitch as it passes you, just happening to light instead of sound. Keep falling and the black hole starts playing tricks on your eyes. For the first 10 minutes, it actually looks like it's getting farther away even though you're racing toward it, an optical illusion caused by the way light bends around a source moving that fast. Then, at some point, you cross the photon sphere, the point where light itself is forced into orbit around the hole. Once you're here, any light coming from outside has no choice but to fall in with you. 24 seconds later, you cross the event horizon. There's no flash, no wall, nothing to feel, but that's it. There is now no path back to the universe you came from. From here, things get fast and violent. A force starts stretching your body, head one direction, feet another, because the pull on the part of you closer to the center is so much stronger than the pull on the part farther away. Physicists actually call this spaghettification. It's a real term used in real papers for a real way to die. And then, nothing. Physics runs out of answers. What's actually at the center of a black hole is called a singularity, a point where the equations of general relativity simply break down. Nobel laureate Roger Penrose has been blunt about it. Nobody currently knows how to describe what happens there. It's one of the last true blank spots on the map of physics. Here's the twist though, and it's the reason this video exists. A growing number of physicists don't think of black holes as prisons anymore. They think of them as the sharpest telescope we've ever pointed at reality itself, maybe even the most powerful natural quantum computer in the universe. Some now call them the key to understanding how everything works. To see why, we need to go back to 1916 because the story of what's really inside starts with an accident. A physicist named Karl Schwarzschild, serving in the German army, calculating artillery trajectories in his spare time, found the very first exact solution to Einstein's equations, just weeks after Einstein published them. That solution described the simplest possible black hole. But nearly 20 years later, Einstein, working with Nathan Rosen, realized they'd only been looking at half the picture. The full solution didn't describe one universe with a hole in it. It described two universes stitched together at the horizon. A bridge. Today we call it the Einstein and Rosen bridge, or a wormhole, and mathematically it connects our universe to a completely separate one on the other side. The catch, and it's a big one, is that this bridge collapses and rips itself apart faster than anything, even light, could ever cross it. It's a door that exists and is welded shut the instant you touch it. Here's where it gets genuinely strange. In 1963, mathematician Roy Kerr finally solved the much harder problem. What does a spinning black hole look like? It took nearly 50 years after Schwarzschild, because the math is brutal, but the result rewired how physicists think about the inside of black holes. A spinning black hole's singularity isn't a point, it's a ring, and that ring changes everything because if you approach it from the right angle, you can actually miss it entirely. Fall into a Kerr black hole the right way, and instead of hitting the singularity, you pass through the ring and come out somewhere else. Not through open space, through another universe. The full mathematics of a spinning black hole describes not just one extra universe on the other side, but an infinite stack of them, layered like Russian nesting dolls, each one connected to the next by its own black hole, its own bridge, its own white hole spitting you out the other side. Some versions of the math even allow closed loops in time, paths that curve back around to before you started. Now, the honest caveat, because it matters, almost no physicist thinks this actually happens inside a real black hole. Real black holes form from collapsing stars, not from perfect, eternal, idealized math, and that messy, real-world collapse is expected to seal off these exotic passages before anything could use them. Stephen Hawking even proposed something he called the chronology protection conjecture, the idea that the universe has built-in safeguards specifically to prevent this kind of time travel. But the fact that the equations allow it at all tells you something. General relativity is far stranger and far richer than objects fall down. In 1974, Stephen Hawking dropped a bombshell that's still reshaping physics today. Black holes, he showed, actually radiate, faintly, but they do. It comes down to quantum weirdness at the horizon. Empty space is never really empty, it's constantly fizzing with particle pairs popping in and out of existence. Right at the edge of a black hole, one particle in a pair can fall in while its partner escapes, and that escaping particle is Hawking radiation. The bigger the black hole, the colder it is. A black hole the mass of our sun would sit only a hair above absolute zero. But it means black holes aren't eternal. They slowly evaporate, and that discovery cracked open one of the biggest questions in physics. When a black hole finally evaporates away completely, where does all the information that ever fell into it actually go? If you threw a book into a black hole and waited for it to evaporate, Hawking's original math said you'd be left with nothing but featureless, random radiation. The information in that book gone forever. That's a huge problem, because physics is built on the idea that information is never truly destroyed, only scrambled. The resolution turned out to be one of the strangest ideas in modern science, the holographic principle. The amount of information a region of space can hold isn't determined by its volume, it's determined by the area of its boundary, which means everything happening inside a black hole can, in principle, be fully described by information smeared across its surface, like the world's most complex hologram. This wasn't just a nice metaphor. In 1997, physicist Juan Maldacena published what's become one of the most cited physics papers ever written, showing a precise mathematical link between a universe with gravity inside a region and a completely separate description without gravity, living only on that region's boundary, two totally different pictures of reality, both equally true, both describing the exact same physics. Push this idea to its logical end and you land somewhere genuinely mind-bending. Space itself might not be fundamental. It might be emergent, built moment to moment out of countless particles quantum entangled with each other, the way pixels build a picture. Some physicists now describe the universe as something closer to a vast quantum computer, running reality as its output, with gravity itself as almost a side effect of information being processed and connected. Which brings us back to that black hole you imagined jumping into at the start of this video. From outside, you're incinerated at the horizon, your information smeared into radiation. From inside, you fall on, untouched, toward the singularity. Both descriptions are true, neither cancels the other out. That's not a contradiction physicists are still trying to fix. It's one they've come to accept as a real feature of how reality works. So, is there really a door to another universe inside a black hole? The honest answer is, probably not one you could ever walk through. But the fact that the equations even allow the question is what makes black holes, in the words of the physicists who study them, the key to understanding the universe. They're not gravity's dead ends. They might be the closest thing we have to a window into what reality is actually made of. This video pulled heavily from Brian Cox and Jeff Forshaw's book Black Holes, The Key to Understanding the Universe, full credit and a recommendation in the pinned comment. If this changed even slightly how you think about the night sky, Subscribe, there's a lot more of the universe left to get through. See you in the next one.